Hey, good afternoon. Today I'll go through chapter 4, so this normal approximation at the mode, what Laplace did derive and used first. A bit of large sample theory, not that much on the during the lecture. So you can also read that section. And then there's a lot of focus on counterexamples, because these are also relevant in other cases than just when doing normal approximation or why large sample theory doesn't hold. Bit of frequency evaluation, and then if there's time, I'll talk about kind of the bit of comparison to frequency statistics, things like that. And if I don't have time, then it's going to be next Monday. So the main thing today is that often the posterior converges to normal distribution when n goes to infinity. So n is now the number of observations, and so when we get more and more observations, it's likely that the posterior is closer and closer to normal distribution. This often is that one has to be that the number of parameters in the model is not increasing at the same speed as the number of observations. There are also a lot of these latent variable models where there can be latent variable for each observation. And then the number of latent variables grows with the same speed as the number of observations, and then this doesn't necessarily hold. And then there are also many of these counterexamples I will also discuss later. But in these kind of regular models, where the number of parameters stays, for example, constant, and then we get more observations, the posterior tends to get closer to normal distribution. And you read already in chapter 2, there was this example of inferring ratio of girl and boys born in Paris, and then Laplace couldn't solve this incomplete beta integral, and then derived this normal approximation to be able to then compute the probability that whether this ratio is larger than half. Then kind of the even it was already useful for Laplace, and there's been many people who have contributed in the theory to show that which conditions need to be fulfilled that this happens, and the most strict proof is then from 1950s Lecam, and there's also been then later advances kind of extending it to different types of cases. You already seen this example before when I was discussing importance sampling. And so this is the BioAssal example where the first row shows the posterior distribution for alpha and beta. We have posterior draws, the blue dots, and using posterior draws, it was easy to compute this LD50. What is the concentration that would kill approximately half of the rats? And we get the uncertainty as a histogram. And now we can clearly see that this distribution is not yet normal distribution, and then but then on the other hand we had only 4 groups of rats. And then the bottom row shows the normal approximation to that anyway. And so that we can approximate these posterior distributions even before we have infinite number of observations, we can approximate them with the normal distribution. One way to look at this is that we can think about also that what is the logarithm of that posterior distribution and what is the logarithm of normal distribution. And if we take logarithm of normal distribution, we get just that quadratic term, and so it is just the second order polynomial quadratic function which we need to find. This can be also considered that we find the mode, so theta hat, and then we make a univariate Taylor series expansion around the theta hat. And we know that the Taylor series expansion is, given that we get enough terms, we can model smooth functions with arbitrary accuracy. It doesn't matter what smooth function it is, as a continuous function with certain smoothness properties. We can just add more and more terms and we get more accuracy. But now when I specifically say that, okay, let's make this Taylor series expansion around the mode, we know that at the mode the first derivative is 0, so we can drop that term. And then these asymptotic results, large sample theory results, so that, again, this often refers to these that regular models, fixed number of parameters, that when n goes to infinity, then these higher order terms are small. They are not necessarily, of course, when we go to infinity, they get closer and closer to 0, but it can be also in a finite case, often they are small enough that we get useful approximations with just these 2 terms in this Taylor series expansion. And correspondingly, we can extend this to multivariate series. And again, at the mode, the first order derivatives are 0. And then we need to focus on the second order derivatives. And then with the Taylor series expansion, specifically for the log posterior, then the first term is just the log density at the mode, and the second term is then the second derivatives of log density at the mode. And then this corresponds to multivariate normal. Multivariate normal having then this covariance matrix sigma, which is then comes from the second derivatives. I still use the Bayasa example. Here's an example showing kind of a case where the normal approximation could be, in a way, it's not perfect, but it's already quite close to something useful. In the upper left plot, we have the true posterior, and then I've just added blue lines showing kind of slices, which are then shown as the blue lines in the bottom ones. So the top figures show the joint density, and then the bottom ones then show, on the left-hand side we have conditional density, given that beta is fixed, so corresponding to the slice along the horizontal blue line or horizontal red dashed line. And on the right-hand side, there's the conditional density if alpha is fixed, corresponding to vertical blue line or vertical red dashed line. And so you can see that, those lines, they go through the mode. And we can see then that for the conditional distribution for alpha, it is actually quite symmetric. But for the beta, we can see that the true distribution is skewed, and then the Gaussian approximation is not perfect. And this was, for the beta, that was the how quickly increasing the dosage, how quickly kind of then the probability of rat dying increases. And now this data had enough information saying that it's very unlikely that beta would be less than 0. So there was strong information about that. And then it means that here it's skewed because the true uncertainty, so the posterior distribution stays at the in larger values than 0 for beta, and then the Gaussian approximation is not handling that as well. And then specifically now for the LD50, we needed to compute alpha divided by beta, and even if this, in a way, it's not that much shifted, the Gaussian approximation, but when we wanted to know alpha divided by beta, the error near 0 is actually very important. So the normal approximation is putting too much mass near 0, dividing with something which is near 0, we get very large values. So here it has to be remembered also that when we do this approximation, that it matters what is the our final quantity of interest. Also in this model, if we would get more and more observations, one thing would be likely then that this the true posterior would also get narrower, and when it's narrower, it's relatively further away from 0, and it starts to get more and more symmetric. And then it's easier and easier to model with normal approximation. This shows also these corresponding log densities, so quadratic functions. It shows in more detail the difference in tails. So it happens that for alpha, it happens to be that the quadratic approximation for log density is good also further away. And here we can see there's a bigger problem. The log density goes steeply down the true, and then the quadratic approximation is not able to handle that. And this is now the normal approximation. Only information it is now using is that it's finding the mode, and then at the mode looking at the local curvature. And you can see it in here specifically that it's only what's the curvature there, but it doesn't know that actually after that it starts, the true function drops much faster down. The kind of the benefit that why it is interesting that then the distributions, when we get more observation, tend to go towards normal distribution is, of course, that there's it's computationally much faster to find the mode and compute the Hessian there than do, for example, Markov chain Monte Carlo integration. If you think about the when we use Hamiltonian Monte Carlo, we are computing their log densities and gradients. We often take thousands of posterior draws, and each posterior draw is likely that we've been doing dynamic simulation at least 10 leapfrog steps. So it's likely that we've done tens of thousands of log density and gradient evaluations. At some point when we have big models, a lot of data, it's possible that each log density evaluation takes more time. But then with the optimization, if the posterior distribution is close to normal, there are efficient optimization algorithms which can find the mode. Usually not many more steps needed than what's the dimensionality of this posterior distribution. And well, for specifically in this example, since there's only 2 dimensions and this is easy, I think it's something like less than 10 log density evaluations and gradient evaluations to find the mode. And at the mode, we might have analytic solution, but even if we would use, if we have a gradient, so what we have from Stan using Autodiff, and then finite difference to get the second order derivative, it's still like around 10, 15 log density gradient evaluations in this case. Of course, when we have more complex models, it can be more, but usually this optimization and computing Hessian, it's so much more efficient than sampling that it's interesting if we know that in some cases we can use this. Traditionally, of course, this normal approximation has been used also at the time when statisticians did not have that kind of computers as physicists, so that they couldn't run any MCMC, any Monte Carlo, and they had to do this very simple. It was very important, these normal approximations, and sometimes, of course, kind of intentionally going for models where you can have also analytic solutions and provide reasonable accuracy with normal approximation. And the normal approximation is also still commonly used as part of certain models. I'll come back to some of the examples later. So there was the additional term here in this slide. So this again showing the Taylor series expansion. There's the multivariate normal, and that multivariate normal specifically now that we get this observed information, which is the second derivatives, the minus second derivatives of log density. And it's called observed information in that way that this term gets larger when you get more information. And then in the normal approximation, since we have the inverse then it means that the covariance is getting smaller.
Is this same as precision, but precision is like squared?
Yeah, so observed information is same as precision. So this observed information describes the curvature at the mode, and then we also know that if the mode is inside the parameter space, then this is positive, and if theta is vector, then we have a covariance matrix, so it describes also the correlations between parameters. So in the chapter 4, there's an example where it is easy to compute these first and second derivatives, and there's even easy analytic solution to find the mode. Book about how to compute these analytically, but otherwise we would use iterative optimization to find a mode. We use gradients, autodiff or finite difference for gradients or Hessian is also fine. There's demo 4.1 showing that, so we can write the bias log density, and then we can use just optimization function optim. In this case, there's an argument gr for gradients, but if we give null, it means that we are not providing those, and then the optim function uses finite differences. And we are also saying Hessian true, so that we ask it to return also the Hessian. We get from the optim results, we get theta hat and sigma by calling solve, which computes the inverse of the Hessian. So there's another name for the observed information, the Hessian. Arstan ARM has also option algorithm optimizing, so there's examples where if we would have linear model or generalized linear model with very big n, we can use optimizing to find the mode. And it also computes the Hessian. So in Arstan ARM, it's using LBFGS quasi-Newton optimization algorithm, which uses gradients, and it gets gradients from the autodiff, and then at the mode, it uses finite difference of gradients to compute the Hessian. It has the normal approximation, but then it just gets posterior draws from that normal approximation and gives them back as the usual draws. Second order autodiff is coming to Stan at some point, so it might make it this faster, but it's the finite difference of gradients to compute Hessian is also quite efficient. I did also already talk about this, that doing this optimization and computation Hessian requires usually much less density evaluations than MCMC, and in some cases accuracy is sufficient. In some cases accuracy for conditional distribution is sufficient, so when we have hierarchical models, it's likely that in hierarchical models the joint distribution is not close to Gaussian, but specifically these Gaussian latent variable models, such as Gaussian processes, Gaussian Markov random field models, are such that, for example, we may have these kind of spatial models where we assume that there's some spatially smoothly varying function which we don't observe directly. We can have Gaussian process or Gaussian Markov random field prior on that latent process. If we would have Gaussian likelihood, we would have a Gaussian prior, multivariate Gaussian prior, and Gaussian likelihood, and we would have an analytic solution. But if we use these multivariate Gaussian priors with non-Gaussian likelihood, we have the problem that there's no direct analytic solution, but this normal approximation can be still used. And then these latent values could be integrated using normal approximation, and other higher level parameters then can be integrated, for example, using MCMC. Accuracy can be improved by importance sampling. And here's an example I did so when I was talking about importance sampling. So the first one, just evaluating the density in grid, then sampling based on the grid cell probabilities, normal approximation. And now here, with the normal approximation, there was the problem that we have too much of the approximation mass near zero. When we draw posterior draws from the normal approximation near zero, and then when we compute LD50 minus alpha divided by beta, we get specifically much longer tails because we are dividing too often with some very small value. And there was, if we just look at the how accurate our approximation for LD50 is, that standard deviation of LD50 approximation is 0.1, and then the standard deviation from the normal approximation for LD50 estimate is 0.75, so much bigger, so there's clear error. But with the importance sampling, we can get similar standard deviation. We know that it's not perfect. Still you can see just by eye that there's a difference between which one is from the grid, which is normal approximation with importance sampling, but it's enough that it's specifically removing those the mass near zero, making the LD50 posture better. In bioSI example, so we can use the Pareto K diagnostic as discussed when I was talking about importance sampling, looking at the distribution of the importance weights, and in bioSI example diagnostic it is good. I did mention that Arstan ARM has this algorithm optimizing, and since last October it has also, when you are using optimizing, this Pareto K diagnostic and importance resampling. When we are doing importance sampling, we could compute these estimates also so that we have these weights included. So some expectation of theta. So we could have these importance weights included there, but then it is easier for further analysis and visualization to do importance resampling, which was already what happened also here, that we have the normal approximations, and then using the relative probabilities from the importance weights, we draw again from that set of these draws from the normal distribution, and in this figure in the bottom row you could see some of the dots are clustered together. So in that case, we were drawing one of the proposal draws from the normal distribution several times. But it helps then that it's now then easy, instead of then for the further analysis needing to keep these weights. For example, how do we draw a histogram if we would have weighted draws? It's easier to draw a histogram if we do the resampling. And so the resampled draws, they have equal weights. It's just that we have then repeated draws in those regions where the weights were bigger. And so this is also then in Arston ARM if you happen to have some point have case where MCMC is too slow. And of course, so oops. Accidentally pressed home. And so in Arston ARM, this is also only applicable for non-hierarchical models. For hierarchical models, the Gaussian approximation is unlikely to work. In future, there will be available the normal approximation at the lower level, so that also in hierarchical models with Gaussian priors and non-Gaussian likelihoods, we can do integration over these latent values or part of the parameters, and then rest part with MCMC or optimizing, making it more efficient. The book chapter doesn't mention, but we can improve over normal approximation. We could use also higher order derivatives at the mode. This is very rarely used. It gets more complicated, and also, so one thing is that if we use higher order derivatives, you can think it as we are using higher order polynomial fitting for the log density. The quadratic was in that way good that in log density the quadratic tails keep going down. If we have third order polynomial, for example, there's a possibility that we could get better fits, but we could get also something like this, that far in a tail this is not anymore constrained to be going down, and so these higher order derivative approximations are more complicated, and in higher dimensions even more. More common is then to use split normal. Split normal is such that we can, so if we would have otherwise quadratic, so if there's a mode and we have a quadratic that would be symmetric, we can have quadratic which is in other direction has different parameter so that it goes down slower. And then if we think about, so if this is for the log density quadratic, this means that this is then Gaussian, goes down faster on other side than on the other side. And we can get skewed distributions with that. Using student D distribution, we can get thicker tails, which can also improve importance sampling. These are a bit more commonly used than these higher order derivatives, but not still they still add a bit more computational complexity, and they still are limited that in higher dimensions, even small differences between approximating distribution and the true distribution makes it difficult to get match between the typical sets, and it's unlikely that the distribution of the importance weight gets bad in high dimensional cases. But instead of mode and Hessian at the mode, it's much more common than kind of changing these distributional approximations. Variational inference is very common in machine learning. And then chapter 13 discusses variational inference and expectation propagation. It's been very common also there to use just the Gaussian approximation because of the computational issues. There's recent advances of using more complex distributions, specifically automatically. Of course, there's been different distributional approximations which have been kind of hand-selected for specific cases before. Combinations of exponential family distributions have been used also before, but making these things kind of automatic it's more difficult. Speed of these is usually between like finding the mode and doing the normal approximation there, and between MCMC. It's also that, so the expectation propagation is and variational inference both for the Gaussian latent variable models works quite well. Expectation propagation is from these the better one. Most of the use of variational inference in machine learning is such that the posterior approximations are actually quite bad, but it is such that in those cases at least doing a bad approximation is still much better than just optimizing. And so in a way that the most of the discussion of like Bayesian deep learning or using variational inference, also the ADVI in Stan, it was in the beginning advertised like too much that in a way that it's really great, while as a posterior approximation it can be really terrible. And yes, at the same time it is possible that like in neural networks even really terrible posterior approximation can be better than just optimizing. Here's an example with the how typically these change that if we use for example just a normal approximation with some different criteria to optimize than the finding the mode and Hessian. So you can see now that this with the variational inference the shape is the same, but it has moved so that it's kind of covering more of the relevant mass. There's still a bit of problem that the left hand tail that it's a bit too long, but otherwise it's also kind of that the mean of the approximation and the true distribution are closer to each other. And we can compare here again how this variational inference would perform. So these were before the grid sampling and the normal at the mode and normal at the mode plus important resampling results. And here's then the variational inference And so here already the variational inference, even without the importance sampling correction, gets much better result for the LD50. And then after importance resampling, about the same as with the other normal approximation. And we can see also with the Pareto K, diagnostic says also that then this approximation is better. This is now misleading in that way that this is only two-dimensional example. Variational inference works well. Let's say in less than 20 dimensions, it's easy to get cases where we get good enough proposal distribution for importance sampling able to do the correction. But when we go to higher dimensions, you can think about the deep learning where there's millions of parameters, then these variational approximations cannot be anymore corrected with importance sampling. It's already likely that with the 100 parameters, we are not able to correct with importance sampling the variational inference. Of course, there are specific cases where it is possible, and combinations of these, like Gaussian prior and exponential family likelihood, is where the posture is likely to be Gaussian.
Just a quick question.
Yes?
So over here, the normal at mode versus normal with VI. So normal with VI does slightly better than normal at mode, because then it gives lesser mass near zero. So then the weights would be not as high compared to correct? Or is there anything else also? So I'm looking at the second figure.
Yep.
The green plot versus the red plot. So the red plot has much more whatever mass near zero, and the green one is much narrower near zero, closer to zero.
Yeah.
So then the importance weights, the ratio alpha by beta in LD50 would be, there would not be as many high weights in the green one compared to the red one. That's why VI for S.
So the more important part is what's happening on the large beta values. So the modal normal approximation, it gets down too fast for the large beta values. And then there we have really large weights. And then the variational approximation has the tail matches better the large beta values. So in a way that so the modal approximation was itself bad near zero, but that part was easy to correct with importance sampling. So that with the importance sampling, it's easy that if we just make some of the weights really small, but it's more problematic that if some of the weights are really large. And so the problems are on the right-hand side. Okay, let's have 10-minute break, and then I'll continue with the large sample theory and the counterexamples.